Wow, 19th century and Sir Balmer using a laptop. He used to be one hell of a scientist. Ain't that true, Sir Balmer?
I think it's time to let the world know about this discovery of mine. I believe it will change the world and give a new direction to quantum theories we are aware of, and also can change the way we see the particle as.
So this is the formula given by Sir Balmer for wavelengths of different colors in Balmer's series of hydrogen atom.
Greetings, Obama.
You can take this with you.
Meanwhile, in Sweden.
I don't think this formula is working. It might be mathematically correct, but it's not giving me any viable result. I really don't know what to do now.
A few moments later.
Come in.
Sir, have you seen this new theory given by Sir Obama this year? This could prove to be useful for your research.
I think he's right. I think I can really put this formula to my use.
More moments later.
Obama seems to have done a really good job. But guess who did it better?
So this is the famous Rydberg formula we all know about, where lambda is the wavelength of the light, where n represents the principal quantum number for energy levels of an electron, with nf being final energy level and ni being the initial one, and Rh is the Rydberg constant, as shown. In the experiment to find the Rydberg constant for an hydrogen atom, we use the Balmer series because it lies in the visible region of light spectrum. Here, Ni becomes 2 and Nf varies with the wavelength for each color. First, we check that the slit is directly visible through the eyepiece when the telescope and collimator are aligned. Then we place the prism on table and observe the slit. So, as you will see, the slit is visible after the prism was placed. So, this is how we perform the minimum deviation part by rotating the prism table and adjusting collimator and telescope respectively. After performing the minimum deviation part, we are done with the Schuster's method.
So, for the experimental setup, after focusing both telescope and the collimator of our spectrometer using the Schuster's method, we place the grating in the hydrogen lamp as shown and observe the colors through the eyepiece of the telescope. Now, for different colors, angles of diffraction will be different. And now using the grading formula, which is lambda is equals to d sine theta by n, where d represents grating parameter, which is known to us, and n is equal to 1, as we observe only the diffraction pattern of first order. So we obtain lambda for different colors observed through the telescope. Now, by taking the value of nf for the particular color observed and ni equals to 2, we can calculate the value of our Rydberg's constant.